We have been working with the following equation. Delta G is equal to standard state delta G plus RT natural log of the reaction quotient Q. We used this equation in our electrochemistry lab, except that we expressed it in terms of the cell voltage, and since delta G is equal to minus NFE, we can write this equation as minus NFE equals minus NF E naught plus RT natural log of Q, which leads us to E is equal to E naught minus RT divided by NF times the natural log of Q. So the Nernst equation is the same as this equation for delta G. Regardless of whether we're using the cell potential or delta G as a measure of the spontaneity of the reaction, we can use this equation to come up with an equation for how the equilibrium constant is related to the standard state value of delta G, or the standard state value of the cell potential. Remember that at equilibrium, we know that delta G is equal to 0 and the cell potential are equal to 0 when we're at equilibrium. And so we see that at equilibrium, we can write that 0 is equal to delta G naught plus RT natural log of K in this case, because at equilibrium, Q is equal to K when we're at equilibrium. So we can rearrange this equation to write that delta G naught is equal to minus RT natural log of the equilibrium constant. And we can rearrange that to solve for the equilibrium constant K. And when we do that, we end up with K is equal to E to the minus delta G naught divided by RT. So K is a function of temperature, and it's not only a function of temperature through the fact that temperature shows up here in this equation, it's also a function of temperature because delta G itself is also a function of temperature. Remember that delta G, any delta G, so also delta G naught, is equal to delta H naught minus T delta S naught. And so we can see that delta G naught is also a function of temperature. And so this value of the equilibrium constant depends on temperature in a complicated way, because there's a temperature here and delta G itself is temperature dependent. So let's see how K depends on temperature. So to figure out the overall temperature dependence of the equilibrium constant, we're going to need to plug in our expression for delta G into our expression for K. So when we do that, we end up with K is equal to E to the minus delta H naught minus T delta S naught, the whole thing divided by RT. So we can rearrange these terms in the exponential a little bit, and we end up with K is equal to E to the minus delta H naught divided by RT times E to the delta S naught divided by R. To do this, I've taken advantage of the fact that the exponential of one term plus another term is equal to the exponential of the first term times the exponential of the second term. So the overall temperature dependence of our equilibrium constant can be expressed in this way. Let's do a little bit more algebra on this and see if we can write this in a straight line y equals mx plus b form. So to do that, we have exponentials, and so it seems like it might be useful to take the natural log of both sides of this equation. So when we do that, we get the natural log of K is equal to minus delta H naught over RT plus delta S naught over R. So if we imagine that we have measured the equilibrium constant at a bunch of different temperatures, we can see that this is in the form of a straight line. Let's write our natural log of K is equal to minus delta H naught over R times 1 over the temperature plus delta S naught over R. If we do it this way, then if we use the natural log of the equilibrium constant as y, that will be equal to some slope value times x. So if we put 1 over the temperature on the x-axis, plus some y-intercept value. And so if we make a graph of data where we've measured the equilibrium constant, K, and we calculate from our measured values of K, we calculate the natural log of K and put that on the y-axis. And we've measured this at various different temperatures, and we calculate 1 divided by the temperature. Notice that these temperatures need to be in Kelvin, so we put 1 over the temperature in 1 over Kelvin units. On the x-axis, we find that we will get a straight line with a slope of minus delta H over R. So if our reaction is exothermic, then delta H will be negative, and minus a negative will be positive. So we will have a positive slope if we have an exothermic reaction. So when delta H naught is negative or less than 0, that's an exothermic reaction. And when delta H is negative, a negative times a negative makes it positive, and my slope is positive. However, when I have an endothermic reaction, so when my reaction is endothermic, I will have a positive delta H naught, and that positive delta H times this negative will give me a negative slope when I have an endothermic reaction. So endothermic, remember, is when delta H is greater than 0. And when delta H is greater than 0, a positive number times this minus sign makes this a negative slope. So I can tell right away by measuring the equilibrium constant as a function of temperature whether in fact my reaction is exothermic or endothermic by whether my line slopes up or down. Notice that because we have calculated 1 over the temperature, that in fact these temperatures down here are the high temperatures because 1 over a larger number is smaller, and the bigger numbers, 1 over t, are the low temperatures. And so when I look at this graph, I have to remember that 1 over t means that my larger temperatures are over here and my smaller temperatures are over here. So this means that for an exothermic reaction, my equilibrium constant will decrease as I increase the temperature. And for an endothermic reaction, my equilibrium constant will increase as I increase the temperature. In our last lab this semester, you are going to measure the equilibrium constant, KSP, for a solubility product, and you're going to do that as a function of temperature. And you're going to make a graph just like this. Notice that when you put a best fit line through your data, your slope value of that best fit line can be equated to minus delta H naught over R. And so the slope is equal to whatever your value of your slope is equal to minus delta H naught over R. And so delta H naught is going to be equal to minus the slope times R. Notice also that the y-intercept, so if you extrapolate your data to 1 over t equals 0, the y-intercept will be equal to delta s over r. And so if you take your y-intercept value and set that equal to delta s naught over r, you can get delta s naught from your data by multiplying your y-intercept by r.